Hello everyone, I'm Dr. Shaik Ruksana Begam, working as Assistant Professor in Department of Electrical and Electronics Engineering from Institute of Aeronautical Engineering, Hyderabad. Today I am here to deliver a lecture on problems on equivalent resistance calculation. Before solving the problems, first we have to know in the previous lecture what we have discussed. So firstly, we have discussed about how to calculate the equivalent resistance. Basically, equivalent resistance is calculated to reduce the network. If it is a complex network, it will be reduced by calculating the equivalent resistance. The calculation of equivalent resistance is basically of three types. One will be of series. Once they are connected in series, how to calculate the resistance. And second one will be parallel. And third one will be combination of series and parallel. So this we have already discussed in the previous lecture, how to calculate the resistances when they are connected in series. If they are connected in series, first point we have to remember that is, if the current is same across all the resistances, then the circuit will be connected in series. So for example, if all these resistors are connected in this way, then it is said to be in series. And if the current is dividing in the circuit, then it is said to be in parallel. For example, the circuit is connected in this way. So if the supply is given here, the current is dividing here. This is resistor 1, which is the current flowing I1. Here will be I2 and the resistance is R2. Here is R3 resistance and the current is flowing I3. If n number of resistors are connected, then the current flowing across these resistors will be denoted with IM. So if the current is dividing, then it is said to be in parallel. If the current is same across all the resistances, then it is said to be in series. So depending upon the combination circuit, if the circuit is combined, like they have connected in series and parallel, so if these two are connected in series and this will be in parallel with this. So if the circuit is connected in this way, first we have to identify the combinations. So first these two are connected in parallel and these two are connected in series. If the circuit is connected in this way, first we have to reduce the network which is connected in parallel. So these two resistances are connected in parallel. So first we have to reduce these two resistances into a single resistance which will be connected in this way. Again, these three resistors will be in series with this network. So to calculate the series resistance, the R equivalent will be R1 plus R2 plus R3. If there are n resistances connected in the circuit, then it will be of Rn. So if the circuit is connected in parallel, then the calculation of R equivalent will be of 1 by R1 plus 1 by R2 plus 1 by R3, plus if the n number of resistances are connected, then it can be calculated with 1 by Rn. In this way, we can calculate the resistances which are connected in series, and in this way, we have to calculate the resistances which are connected in parallel. If there is a series and parallel combination, first we have to reduce the parallel combination and then we have to go for series. In the previous lecture, we have calculated the sample problems, like simple problems which were connected in series, parallel and series parallel combinations. In this session, we'll be calculating somewhat complex problems which are related to the resistances. Mostly we'll be using resistors in this circuit, so we'll be calculating only for the resistances. So the first example will be, so here is the first example. First, find the equivalent resistance of the following circuit. So here is the combination of series, parallel So first we have to reduce the parallel circuits. First we have to see the circuit. So these two are in series, these two are in parallel, and these two resistances are in parallel, and these two resistances are in parallel. So first, coming from this side, we need to reduce these two parallel elements. So one 1 ohm resistor and another 1 ohm resistor is connected in parallel. So first we have to reduce this circuit. So to reduce the R equivalent, so generally it is taken as R. The formula for this will be of R1 into R2 by R1 plus R2. If the two resistors are connected in parallel, this is the basic formula to reduce the circuit. So here are the two resistors which are connected in parallel. This can be reduced as, so 1 into 1 by 1 plus 1, which will be 1 by 2. The resistance will be taken as 0.5 ohms. So after reducing this circuit, we have to redraw the circuit again, which can be redrawn as, so the resistances here will be as it is, and the resistances here will be connected in parallel. And after reducing this parallel circuit, we'll get a single resistance which is of 0.5 ohms. So the rest of the resistors will be of same, which is of 3 ohms, 3 ohms. And here is the supply. So now we have reduced this circuit and we got the value of 0.5 ohms. Next, moving to the next step, here we are having 2 ohms resistances which two are connected in parallel. After that, we have to reduce this 2 ohms resistances. Again, the formula will be R equivalent is equals to 2 into 2 by 2 plus 2. Which will be of 4 by 4, which will be of 1 ohm resistances. After reducing these two parallel networks, we got the resistance as 1 ohm. Again, we have to redraw this circuit. So again, these 3 ohms resistances are as same. After reducing these two resistances, we are getting it as 1 ohm and 0.5 ohms. And this will be as it is. So now if we see this circuit, here there is no current division. The current flowing in the circuit is same across all the elements. So this circuit is connected in series. So if the circuit is connected in series, the R equivalent can be calculated as R equivalent is equals to 3 plus 1 plus 0.5. So the value will be 3 plus 3, 6, 7.5 ohms. So in this way, we have to calculate such type of circuits. First, we have to see how many parallel connections and how many series connections are there in this circuit. Depending upon that, we have to calculate. So if we consider this same circuit, first we have to see how many parallel connections are there. First, these two are connected in parallel. So first we have to reduce these two networks. After reducing these two networks, first for the first network, we are getting the value as 0.5, and for the second network we are getting the value as 1. After redrawing the circuit, all these 4 resistors will be connected in series because of there is no current division. The current flowing across the circuit is same across each element. So I have already mentioned, if the current flowing in the circuit is same, so the circuit will be connected in series. So all these 4 resistances will be connected in series. So to find out the R equivalent, we need to add all these 4 resistances, which is of 3 plus 3 plus 1 plus 0.5. The R equivalent will be of 7.5 ohms. So moving to the next problem. So here also there are combination of series and parallel networks. So the question is given as find out the equivalent resistance of the following circuit for across the points A and B. So across these 2 points, we need to calculate the equivalent resistance. In the same fashion, first we have to see how many parallel connections are there, and next we'll be moving for the series connection. After that, we need to calculate. So first, here there are two parallel connections. One is of connected in this way, and another one is connected in this way. So first we have to reduce the parallel connections first. Before reducing, first we have to see whether the current is dividing. So if the supply is given here, the current is flowing in this way, and it is dividing here, again it is dividing here, and the current is moving back to the position. So here the current is dividing. So these two connections are connected in parallel. So if we see this here, 4 and 2 ohms are connected in series. So first we have to reduce that network. So if these two are connected in series, we need to calculate as 4 plus 2, which will be taken as 6 ohms. Again we have to redraw the network. So it can be redrawn as the resistance is 8 as same, and here is also 8, it is of 6 ohms. So again two resistors are connected in parallel. So bring one series resistance. So we have to calculate the resistance across the terminals A and B. After that, again we have to reduce the parallel combination. So these two networks are connected in parallel, and these two elements are connected in parallel. So we can reduce either this or this. According to our wish, we can reduce this network or this network. But first I am preferring 8 and 6 ohms resistances. So it will be of 8 into 6 by 8 plus 6. So the value of 8 into 6 by 8 plus 6 will be of 3.428 ohms. And again after that, I'm reducing 6 into 4 by 6 plus 4. The value of this will be of 2.4 ohms. So after reducing these two parallel networks, the value whichever we got is after reducing this network, it is of 3.428 ohms, and this will be of 2.4 ohms. So again we have to redraw the network. So it can be redrawn as new resistance, the simple resistance, two series resistances, and we need to calculate the equivalent resistance across the terminals A and B. So here the resistance is taken as 8 ohms, and here it will be of 6. The value is 3.428 ohms, and here it will be of 2.4 ohms. So now if we see this combination, here the two resistors are connected in series, and these two resistors are connected in series. So before solving the parallel combinations, first we have to reduce these two series networks, which is of 8 plus 3.428 is one combination, and another combination will be of 6 plus 2.4. So after reducing this, we'll get 9, 10, 11.428 and 8.4 ohms. So after reducing this two series network, I'm redrawing the circuit. Again, the resistors are connected in this way. So the first resistance value will be of 11.428 ohms, and the second resistance value will be of 8.4 ohms. Now we need to calculate the equivalent resistance across these two terminals, which is of A and B. So now coming to the last circuit, these two elements are connected in parallel because the current is dividing here. So if the current is dividing, the network is said to be connected in parallel. So if the two resistances are connected in parallel, we'll be using R equivalent is equals to R1 into R2 by R1 plus R2. So to reduce this network, we'll be calculating 11.428 into 8.4 by 11.428 plus 8.4. The final R equivalent will be taken as 4.841 ohms. So this will be the final equivalent resistance across the terminals A and B. The final resistance will be drawn as, these are the two terminals which are A and B. The final resistance will be of 4.841 ohms. In this way, we need to calculate. First, we have to see the parallel combinations and series combinations. First, we have to reduce the parallel combinations and then we need to move for series. So, till we have to calculate to get a equivalent resistance in the last. So, moving to the next problem. So here the question is given as find the equivalent resistance of the following circuit across the terminals A and B. Here also in the same fashion we need to find the combinations. First, these two resistors are connected in series combination and these two resistors are connected in parallel combination and these two are also in parallel. So how can we say these circuits are in series and parallel? Means I already have mentioned if the current is dividing in the section, so the circuit is said to be in parallel. If the same current is flowing out of the circuit, then this connection is said to be in series. So we have to calculate the opposite side of the supply. So I'm considering this circuit first. First, this circuit is connected in series. First, we need to reduce this circuit and then we have to move for this parallel combination. Again, we have to reduce this parallel combination. We'll get a single resistance that will be in series or in parallel with the resistance depending upon the reduction of the circuit. After that, we have to reduce. If these two are in series, we have to add, and if these two are in parallel, we have to multiply. As we know, R1 into R2 by R1 plus R2. By using this formula, we have to reduce the circuit. Again, after reducing this circuit, again this will be in parallel or series depending upon the connection. So first, we'll solve this two resistances which are connected in series. So firstly, these two are in series, so I'm adding this 4, okay, we'll take it as 4.0 plus 6.0 which will be of 10.0 which can be taken as 10 ohms. So after reducing this circuit, we can redraw the circuit in this way. So the resistance here, it will be as it is. Okay, I'll redraw here, which is 4 plus 6 will be of 10 ohms. So this resistance will be as it is and here. So the reduced series network will be connected in parallel with this circuit and other resistance will be taken as it is, which is of terminal A and B. So here the resistance value is taken as 10 ohms. Here it will be of 3.0 ohms and here it is of 9.0, 8.0 and the calculated resistance will be of 10 ohms. So now we have reduced these two series networks. Now we'll move for this parallel network. So these two are connected in parallel as if the current is dividing here. So these two are connected in parallel. So to reduce these two elements, first we have to take the formula as R1 into R2 by R1 plus R2. So by using this formula, we have to reduce this circuit, which will be of 9.0 into 8.0 by 9.0 plus 8.0. So the value of this resistance will be, value is 4.235 ohms. So again we have to reduce this circuit. So the circuit can be redrawn in this way. So I'll draw here. So after reducing that parallel circuit, we'll be getting a single resistance. Already here is a resistance which is of 10 ohms already connected in parallel. Here the value will be of 2.35 ohms. And here it is of 3.0 ohms. Again it will be of 20.0 ohms. We need to calculate the resistance across these two terminals, which is denoted with A and B. So now we have to reduce these two parallel combinations, as if the current is dividing here. These two are said to be in parallel. Again we have to multiply these two resistances, which can be taken as 4.235 into 10 by 4.235 plus 10. So I have written this equation according to the parallel combinations, which is taken as 4.235 into 10 by 4.235 plus 10. The value will be of 2.951. So after reducing this circuit, the value will be of 2.975. So again we need to redraw the circuit. The circuit can be redrawn in this way. So this resistance will be of 2.975 ohms, and here it will be of 0.3, and this resistance will be as it is, which is of 20.0 ohms, and the terminals will be of A and B. After reducing these two parallel networks, we'll be getting the value which is of 2.975 ohms. It can be redrawn with a single resistance. The value of the resistance will be taken as 2.75 ohms. And these two, if we see this, so the current is dividing here and the current is flowing same in these two elements. So these two elements will be taken as series. So if these two elements are connected in series, we need to add these two elements, which will be of 3.0 plus 2.975. So the value of the resistance will be of 5.975 ohms. So after reducing this network, the reduced network can be redrawn in this way. So this 20 ohms resistance will be as it is. So again the resistance which we have reduced will be drawn in this way, which the value of this will be 5.975 ohms, and this will be as it is 20.0 ohms. Now we have to calculate the final equivalent resistance, as if there are two resistors in this circuit. If the two resistors are connected in parallel, this I'm saying it is in parallel because of here the current is dividing. So these two resistances will be connected in parallel. So to reduce this network to a single element, we need to multiply these two resistances by using the formula, which is of R1 into R2 by R1 plus R2. So here I am taking the direct values, which is of 20.0 into 5.975 by 0.975 by 20 plus 20.0 plus 5.975. So the R equivalent of the final network will be calculated as 4.60 ohms. So the final resistance equivalent resistance across the terminals A and B will be taken as 4.60 ohms. So this will be the final resistance for this circuit. So for this circuit, the final resistance is taken as 4.60 ohms. So in the same fashion, already we have discussed. First, we need to see the combinations of series and parallel, and we have to see the directions or division of the current. If the current is dividing, then the circuit is said to be in parallel. If the current is same across each element, then it is said to be in series. So if there is a series connection, we need to add the whole resistances. If there are n number of resistance, we have to add all these resistances. If there is a combination of parallel network, like the elements are connected in parallel, so we already know the formula. if there are two resistances or two elements connected in parallel, we need to use the formula R1 into R2 by R1 plus R2. If there are n number of resistors connected in parallel, we need to use 1 by R1 plus 1 by R2 plus 1 by R3 and so on till Rn. So if there is a combination, first we have to reduce the parallel. Depending upon the network reduction, we can take parallel or series till till we need to calculate till we are getting of final resistance value. So in this way, we need to calculate the resistances. So in the previous lecture, we have seen how to calculate the inductances and capacitances when they are connected in series and parallel. So if we consider inductances in the same circuit, so if in this place of in the place of resistances, if we are connecting the inductors, however we have calculated for the resistance, in the same way we are going to calculate for inductances also, as the formulas for the calculation of inductance and resistances are same. So if they are connected in series, the whole circuit or 4 elements we need to add. If they are connected in parallel, we need to multiply according to the network. If there are two inductors connected, we need to use the formula L1 into L2 by L1 plus L2. If there are n number of inductances connected in parallel, we need to use the formula 1 by L equivalent is equals to 1 by L1 plus L1 by L2. Already I have mentioned in the previous video, but it is different. It is opposite for the capacitances. If they are connected in series, we need to multiply the capacitances, like 1 by C equivalent is equals to 1 by C1 plus 1 by C2 till n number of capacitors connected in series. So we have to use the formula 1 by C equivalent will be equal to 1 by C1 plus 1 by C2 and so on till 1 by Cn. If they are connected in parallel, we need to add. So if the two resistors are connected in parallel, we have to add it as C1 plus C2. If a number of resistors are connected in parallel, we have to sum all the resistors, which will be of 1 by, C equivalent is equals to C1 plus C2 plus C3. So it is opposite to the resistance and inductance, but resistance and inductance calculation, equivalent calculation will be same. So by if they are connected in series, we'll be using the same formula, which we have to sum all the resistances and inductances. If they are connected in parallel, according to the connection, if there are two resistors or two inductors connected in parallel, we need to calculate, like we need to use the formula R1 into R2 by R1 plus R2 or L1 into L2 plus by L1 plus L2. So it will be different and opposite for capacitances. You have to remember these points. If it is inductor or resistor, the calculation of resistance and inductance will be same. So if while considering the capacitors, if they are connected in series, we need to multiply. If they are connected in parallel, we need to sum all the capacitances. So the parallel division and series division will be taken with respect to the division of the current. So if the current is dividing in the circuit, then the circuit is said to be in parallel. And if the current is same across each element, then the circuit is said to be in series. So moving to the next example. So the same type of problem in the previous lecture we have calculated for the inductances. So here in this lecture we are going to calculate the equivalent resistance for equivalent calculation for this resistances. So these resistances are connected in the combination of series and parallel. So as I have already mentioned, we have to see first the combination of series networks and parallel networks. Depending upon the network, we need to reduce the circuit. First, if there are, this is the supply. We have to calculate the resistance opposite side of the supply. So if this is the supply, the opposite side of the supply will be taken in this way. So if we consider in this way, first these three resistances are connected in series because of the same current is flowing across these three elements. So the current is dividing here. So the current is coming in this way and it is dividing here. So if the same here it is dividing and the current flowing across these three elements are same. If the current is same, then these three resistors are said to be in series. So if the resistors are connected in series, we need to add all these three resistors. So R is equals to 3 plus 4 plus 3. So the R value is taken as 10 ohms. After taking this value, we need to reduce the resistance. Sorry, we need to reduce the circuit. So here the value of these three resistances will be taken as 10 ohms. After summing these three resistances, we got the value as 10 ohms. So after this, we need to reduce the circuit. A part of this three resistance, all the other resistance values will be same. After calculating these three resistances, this circuit will get a single resistance which will be in parallel with the other resistances. The value of this resistance will be taken as 10 ohms, and here it will be of 10, 10 and 5, 3, 4, 2. So now if we consider this circuit, in the opposite side of the supply, again these two combinations, we can see these two resistors are connected in parallel as if the current is dividing here. So if the current is dividing, we need to multiply, like we need to, so here only two resistors are connected in parallel, so we can use the formula R1 into R2 by R1 plus R2. So directly I am taking it as 10 into 10 by 10 plus 10. The value of this will be 100 by 20. So the resistance value will be of 5 ohms. So after getting this value as 5 ohms, again we have to redraw the network. So the network can be redrawn as, so two resistances. Yes. So after reducing this network, so we are getting the 5 ohms, which will get a single resistance that will be connected in series with this 3 and 2 ohms resistances. In the same way, I have connected these resistances. The value whichever we got is of 2 ohms, and here it is of 3, 2, 10, 5 and 4. So here is the supply. So the current is flowing in this way, and here it is dividing, and the current is not dividing here. The same current is flowing across these three elements. So these three elements are said to be in series. If the current is not dividing, the elements connected here will be said to be in series. So if the elements are connected in series, we need to sum these three elements, which will be of 3 plus 2 plus 2. So the value of this will be of 10 ohms. So after reducing this circuit, again the circuit can be redrawn in this way. So here is the 10 ohms resistance, 10 and 5, 4. Again, if we see the direction of the current is dividing here. So these two elements are said to be in parallel. Again, we have to multiply these two elements and we have to reduce the network. So it will be of 10 into 10 by 10 plus 10. Again, it is taken as 100 by 20. So the resistance will be of 5 ohms. After getting the value 5, we need to redraw the circuit again. So the two resistance here will be as it is, and the resistance after reducing the parallel network will be getting as 5 ohms. Here it will be of 5 ohms and here it will be of 4 ohms. So if we see the current direction, the current is not dividing. The same current is flowing across all the three elements. So again, this network is said to be in series. So if the network is in series, we need to add all these three resistances, which will be of 5 plus 5 plus 4, and the R equivalent will be taken as 14 ohms. So in this way, we need to calculate the resistances if the circuits are connected either in series or parallel or combination of series parallel. If they have given, so now this is a resistance network. If the inductors are connected in the same way, we have already solved in the previous lecture. So if the capacitors are connected in the same way, if these three capacitors are connected in series, we have to multiply the three capacitors and we'll get a parallel capacitor across these two elements. Again, if they are connected in parallel, we need to add. So if the capacitors are connected in parallel, we need to add. If the capacitors are connected in series, we need to multiply. So in the same fashion, we need to calculate the inductances and as well as resistances. So that's it for today's topic. In the next topic, we'll be knowing about the star to delta transformation and delta to star transformation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.